Hello. What we're going to cover right now is characteristic points of a perpendicular bisector. We've been using perpendicular bisectors quite a bit for rotations and reflections, and eventually we'll learn how to use them for translations also. So as I look at this activity and start to follow along, it says identify the type of transformation, state whether the perpendicular bisectors play a role in constructing the transformation, and if so, what role, and finally cite an illustration of the distance preserving characteristics. We'll do a couple of those just to get you oriented to it. And so what you have here is there is some transformation, and the first thing you might want to do, at least this is what I did initially, was kind of go through the transformations that I could possibly have. And so we look at rotations, reflections, and translations. Okay, and sometimes what you need to do is you need to say what they're not. And right now I can basically identify that this is a rotation because if I took my paper and spun it, I'd end up with the same image as I had previously. So at least that gives me like a starting point. But if I truly want to prove that one thing is another, basically what we'd have to do is we'd create the perpendicular bisectors and see what the relationship is. And we learned the other day that a perpendicular bisector will intersect at a point, and that would end up being our rotation and reflection. All the perpendicular bisectors lie on the same line, and then finally we'll show what a translation does with the perpendicular bisectors. So again, this is rotation. How do I know it's not a translation? Well, I can't see any vector that maps point to point that's consistent. So like this vector that would map that point to that point goes up, while this vector maps down. This one went up. So we've got all these vectors that aren't the same length, they're not the same size, and so on, so it's not a translation. A little way to think about a translation that may help you is that translations move shapes exact distances and directions. So it's almost like a joystick. It goes up, or it goes down, it goes right, or it goes left, or some combination of that. You might be wondering, well, how did you know it was not a reflection? Reflection should be the mirror image. So I look at this mirror image, and if I had this line of reflection, that would mean that this point should map that perpendicular distance, maintaining it, and come out over here, which I don't see. So think about mirror image. And since it's not really a mirror image, it's not a reflection. So what is a transformation? It's a rotation. Coming over here to perpendicular bisectors, all perpendicular bisectors will intersect at a specific point. And I'll get to a construction shortly that will validate this. We'll just save the time for now. And then basically it says what distances were preserved. Well, let's just pick one, A to B, A prime to B prime. So that would mean that A to B was the same distance as A prime to B prime. You could also add like C and C prime, D and D prime. And so you could also say the measure of angle ACD is equal to the measure of angle A prime, C prime, D prime. Okay, so that's what they mean by examples of distance preservation. Really, it's the distances, but the angles are also preserved. All right, so the next figure, hopefully you can see that this is a translation. And one of the things that you can look at is that each point moved exactly the same. So each of these, if I was to measure the distance between each of them, I'd notice that it was approximately 1 inch here along that same ray. So are they parallel lines? Boy, they sure look like it. And then approximately 1 inch there, and it would go all along. But the true way to tell that this is, or the argument that you would formulate to prove that this is a translation, is that if I go from point to point, and they're talking about perpendicular bisectors for a reason, is that if I can construct these perpendicular bisectors, perpendicular bisectors end up being parallel to one another. So here's one, and we'll pick one that's really close to it, just so you can see how close they really are to being parallel, even with some potential human error. And so I knew that this was a translation just by looking at it, but I also can now use this as my justification. The perpendicular bisectors are parallel. So what distances were preserved? Let's just call this x, this y, this x prime, this y prime, and we can say that x, y is equal to x prime, y prime. And that's what they mean by that. Okay, but the big takeaway is really what do the perpendicular bisectors do for our translation? Well, they're parallel to one another. Okay. Back to example 3. 3 looks like a rotation. It is a rotation. And what should happen with a rotation is the perpendicular bisectors should intersect at a single point. So let's just grab a couple of them. So this point to this point. Really, just to keep this cleaned up, I'm only going to mark the points of intersection just so I can see what I'm doing. Otherwise, it'll become really jumbled up with lines, as some of you have probably found out. And draw this pencil line. So I have my first one. Let's grab another. And so just keeping track of this. Make it a little bit darker. So my line is from here to there. Okay. And if I was going to check it just to make sure, because 2 lines intersecting is not really unique, but if I could get 3 of them to intersect, that would be pretty unique. So I'll pick the point here, this little V point. And notice the perpendicular bisectors are not actually all on the same line. That's purposefully done. But what's going to happen is that they will all intersect at the same exact point. So I'll mark that point with the pink. Construct this line here. And what you're going to notice, and you probably already knew, is that our point of rotation was this corner. But all 3 perpendicular bisectors, and there's a little difference between them, not a lot, end up intersecting all in the same spot. So all the perpendicular bisectors intersect at the same point. And finally, we get to our reflection. And if I create the perpendicular bisectors to analyze what kind of a transformation this is, we can pick any couple points. Where's the perpendicular bisector going to be? And so the tiny circles are somewhat the more difficult ones. But I have this line to start with. And then what should happen is everything should sort of be, oops, I didn't do a good job with my ruler. Okay, and then every other one should lie on it. So if I were to stretch this out and go from the vertex to the vertex, what I'm going to notice is that these arcs intersect right on that line. And again, even if I go further out, so I take my ruler and I connect these, and you're going to notice that they lie right on top of that line. So they all coincide or are collinear. Okay, so we would just extend it. Remember, this was the result of a bad ruler usage. So what's the takeaway here? Is that the perpendicular bisectors are collinear. Perpendicular bisectors lie on the same line or collinear. Okay, thank you for your time.